Hello and welcome to our last class note videos over 4-14 as we wrap up Unit 4. And today we're going to learn how to do two more types of electron configurations. Electron configurations is a general term for any time that you try or attempt to represent the placement of electrons in an atom. The first one we learned to do was orbital notation. That is the one where we put the arrows up and down representing the electrons, all the boxes with the arrows in them. Underneath the boxes, you put the energy level and sublevel, as well as a superscript showing how many electrons were in the particular sublevel. And we put the numbers above the boxes, which showed really that's the third quantum number, the magnetic quantum number, and it identified a particular orbital, and I'm talking about the numbers above the boxes. This is an example of an orbital notation. Drawing lots of arrows, lots of numbers, lots of superscripts. We saw, however, that really, when we learned to read the periodic table correctly, what we really needed to know was the stuff that was written underneath the box. The orbital notation was especially good way of representing quantum numbers of an electron because we had the energy level number out in front. For instance, this 2 right here is the energy level. The P is your sublevel, so we had the energy level and the sublevel represented right there. And you remember the second quantum number when you were in the P was a 0 or a 1. So the quantum numbers of any of the electrons in these boxes right here would be 2, 1. If we're talking about electrons, maybe in this box right here, we would have a 2, 1, and that's the -1 orbital. So there's your third quantum number. First quantum number is principal quantum number. It was 2. Second quantum number is the number that goes along with the sublevel letter. When you were in the S, it was a 0. When you were a P, it was the 1. When you were a D, it was a 2. F was a 3. So any of the electrons here, again, would be a 2, 1. That second quantum number was called the angular momentum or azimuthal quantum number, and that was abbreviated by the letter L. And then we had the numbers above the boxes. That was the magnetic quantum number. That specified which orbital the electrons were in. And then the fourth quantum number is reflected in an orbital notation by the direction of the arrow. Arrow up was a plus half spin. The arrow down was the minus half spin. So the fourth quantum number, the spin quantum number, was represented by the arrow direction, up or down. So orbital notation was especially useful when we were thinking about quantum numbers, and it better helped us understand the layout of the entire periodic table. But once we understand how to read the hidden things on the periodic table, then really we needed the electron configurations. But doing electron configurations, depending on the size of the atom, could be somewhat cumbersome. So for instance, like right here, we did the electron configuration for zirconium. And what we really found out was for zirconium, once we learned to read the periodic table of elements, for zirconium, what really mattered was the 5, and there should be an S after this, 5s2 4d2. All of this other stuff was not super significant in determining the properties, behaviors of zirconium, or where we would find zirconium on the periodic table of elements. This 5s2 4d2 is really what we needed in order to understand zirconium's behavior and where it is on the table. So with the 5s2 4d2, we could find zirconium right here. It is in the 4d, which comes and gets filled right after the 5s. So here's the 5s2, 4d2, there's zirconium. We know it has 2 in the S, 2 in the D, and we can start thinking about what zirconium would do chemically from just knowing that information. So really all these arrows and everything we drew before before seeing that zirconium had 2 in the 5s, 2 in the 4d, all of this stuff, all these arrows and boxes are not really essential once we know how to read the periodic table of elements. So they stopped doing it. they started doing what they called the electron configuration. In an electron configuration, it's a general term for any way of showing where electrons are. But specifically, there's an electron configuration way of doing it. So what an electron configuration does is just write the stuff we put underneath the box. They stop drawing out all the arrows, all the boxes, and all the numbers above the box. So here's our electron configuration for lead. They put all of this stuff out here. And after doing all this stuff, they asked a question. And this is our electron configuration homework. They asked a question: how many valence electrons does lead have? And we saw here that there were 2 in the 6s. Valence electrons are in the outermost level. There was 2 in the 6s and 2 in the 6p. That's the question they asked us after doing all of this long drawn out electron configuration. So chemists began to get tired of doing this long drawn out electron configuration, when what we're really trying to get to was how many valence electrons it had, because these are the electrons that are going to be involved in lead's chemical reactions. When lead chemically reacts, it's going to involve electrons in the 6p and the 2 electrons in the 6s. So they decided that we no longer needed to do a long, drawn-out electron configuration. So they came up with a way of shortening it. And the way of shortening it goes by several names. One of the names is called a nearest previous noble gas notation, which is also called a compressed or condensed electron configuration. And what they do in a compressed or condensed electron configuration is substitute all of this stuff on the inside. The 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6. They substitute it with the element that has that electron configuration. 2 and 2 and 6 is 10, and 2 is 12, and 6 is 18, and 2 is 20, and 10 is 30, and 6 is 36, and 2 is 38, 48, and 6 is 54. That is the previous noble gas. We just counted that the inside of lead, see, this is the level lead is currently filling, the 6th level. So when we look at lead is on the 6th level. So lead put 2 in the 6s, then it dropped down. Lead had the 4F14 filled, right down here. If you just follow the numbers, 56, 57, 58 through 71. Then lead filled the 5D with 10. The 5D is right up here. The 5D was filled. And then the 6P2. It had 2 in the 6P2. 6S2, we look right up here. 6S2, 5F14 or 4F14, 5D10, 6P2. All the stuff on the inside has nothing to do with the electrons that actually get involved in lead's reactions chemically. So what they do is, in the electron configuration, we call it a previous noble gas notation. You go up to the row above lead. You come on down, and you would start out the electron configuration by writing xenon 54. So we went up to the row above lead, and we realized that the noble gas in the row above lead was xenon 54. So you would replace all the inside of lead's configuration with the noble gas that represents that configuration. And you would still write the atomic number right up here. And what it does is just to let you focus. The nice thing about the noble gas notation is you take the previous noble gas, replace the inside, that whole configuration stuff on the inside, which we call the kernel, and then it lets us focus on the part of lead that's going to be involved chemically. Now you double check. 54 and 2 is 56. 66, 70, 80, 82. So you double check your atomic numbers or your superscripts there to make sure that the electrons match the 82 lead should have. It's just a much, much faster way of doing it. And now we're going to talk about how to do it. This was just kind of an example showing you why we do it. It lets us focus on the part of lead that's going to be involved in chemical reactions. It shortens it up. It speeds it up dramatically. The process of representing the electrons in a larger atom. So now we're taking a look at the nearest previous noble gas notation notes. We will get to diagrams a little bit. Again, this is called compressed or condensed electron configurations. And it's a way of shortening out those long, drawn-out electron configurations so that we can focus on what really matters, the electrons that were recently placed in the valence levels. When doing a noble gas notation, we replace that inner level, which we call the kernel. The kernel is the inside of the atom that doesn't get involved in chemical reactions. And we replace that with the noble gas element on the row above the element we're looking at. So the reason they call it nearest previous noble gas notation is you go to the previous row at the end and find the noble gas that was nearest to it. And that'll allow us to focus on the valence level. How do we do it? We write the symbol of the element we're doing with its atomic number. Then we look at the row above that element and write the noble gas symbol of the element with its atomic number. Usually you put brackets around it. Then you start at that point and just fill in the electron configurations of the remaining electrons that are found on that level that you're doing, which will lead you right up to the element. Let's take a look at doing a noble gas notation for germanium, number 32. First, we write the symbol germanium 32. Then we look at the row above germanium and find the noble gas. So here's germanium. This table is really useful. The off-by order of filling table makes this really easy to do. But here's germanium 32. We bounce to the row above it and go to the end. There's argon 18. So inside the brackets, we put argon 18. Now we're just going to start at argon 18. Remember, when we did electron configurations, we always started at hydrogen number 1. We started at square 1. Well, now we're going to start our electron configuration, the remaining of it, at the element we left off. So here's argon 18. And we're trying to get to germanium 32. So here we go. I just go to the next row. 19 and 20 is calcium. That's 4s. There's 2 elements there, so we would write 4s2. There's 4s2 for germanium. Now we're going to continue. Potassium and calcium are in that 4s2. Now we're going to continue after calcium and go into the 3D. So here's calcium, and now we're going into the 3D, and there's 10 elements in the 3D. We can just count them. 3D10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we would write 3D10. There's 3D10. Now it took us from scandium up through zinc. And now germanium's in the 4p. So it's the second one in the 4p. So we would write 4p2. And then we can check it. Germanium should be 2 in the S, 10 in the D, 2 in the P. So let's see if that's what we would have. Here's our 4p2. And again, we're looking. Did it have 2 in the S, 10 in the D, 2 in the P? It did, just as we were predicted here. 2 in the S, 10 in the D, 2 in the P. Now let's make sure we did another double check to make sure we had no mistakes, is to add up our electrons. Argon has 18, plus 2 is 20, 30, 32. We have germanium number 32 correct. And that's what they're talking about here, adding up the electrons. Let's do another example in the next video.